For tuning in. This is Mingkun Chen. I am a PhD student from the Electrical Engineering Department at Stanford University, and I work with Professor Jonathan Fan. Today, I would like to show you our recent work in using data and physics-driven machine learning to achieve ultra-fast optimization for photonic devices. More specifically, we have applied this idea to the inverse design of metasurfaces. Metasurfaces are artificial media with subwavelength scale patterns that are able to control the propagation of light by wavefront shaping. Inverse design using topology optimization has proven to be highly effective to design metasurfaces with optimized performance. Since we have the tools for optimization, we should always aim for the best device we can possibly design for practical purposes, whether it is for holography, polarimetry, or simply a lens or grating. There have been a lot of groups in the field doing fantastic works. Here I just show some basic examples for inversely designed freeform metasurface devices. And we can see that with topology optimization, we're really able to push the design limits and design metasurfaces with extremely high efficiency. Topology optimization based on adjoint variable method is a well-studied topic and has been applied to various applications for quite a while. First proposed by Ole Sigmund and Owen Miller, it is an iterative optimization process based on gradient descent or gradient ascent. Here on the right, we're looking at the top view of a unit cell of a deflector. We iteratively optimize the material distribution or the shape of the pattern for a certain design objective. During each iteration, the gradient of each pixel can be calculated from a forward and an adjoint simulation, EM simulation. While topology optimization is powerful for inverse design problems, the time and computation cost is a practical bottleneck, as we need to perform large number of EM simulations for the iterative process. Not to mention when we need to perform simulation of large domains and optimization in a very non-convex problem space. To address this bottleneck, people have been looking into machine learning algorithms. For example, here shows some excellent works using deep neural networks as surrogate EM simulators. These studies demonstrate the possibility of using machine learning to accelerate the near-field simulation or simplify the design problem. Of course, these are just two representatives, and there are a lot more interesting studies in the field recently. Inspired by Muskin's work, we developed a unit which can be trained to predict EM fields from a device layout. The unit is a special type of deep convolution neural networks. It is made of an encoder and a decoder. And then shortcut links are used to connect between the encoding blocks and decoding blocks to maintain a strong feature correlation between the input and output layers. To be more specific, the unit here takes in a matrix that defines the dielectric distribution of the device geometry. Then at the end of the network, we have a multi-channel output layer that gives the real and imaginary part of the magnetic field. Lastly, we can calculate all the E-field components by applying a convolution operator according to the discrete Ampere's law. In this study, we use this free-form 2D diffraction grating as an example. Here, each period contains silicon nanoridges on top of silicon dioxide substrate, and the excitation source is TM polarized plane wave. We first tried with a conventional training scheme where 30,000 examples of device geometry magnetic field pairs are first generated with C7J, which is a standard FDFD solver. And then the loss function is formed as the mean absolute error, which measures the difference between the ground truth field H hat and the predicted field H, aka the output of the network. Note that this is a very conventional way of forming the loss function, which is also used as the baseline method for this study. This baseline method gives pretty good magnetic field prediction. Here shows a representative device geometry and its corresponding ground truth field and predicted field. Just eyeballing it is actually very hard to tell the difference. Meanwhile, the unit takes only about 10 milliseconds to solve for the field, while it takes about 2 seconds for a standard FDFD solver. So the unit is more than 2 orders of magnitude faster. So given this level of accuracy in field prediction, will this baseline method work for the optimizer? Before seeing the answer, I will first briefly go through how we form the optimizer. To perform the topology optimization, we first train two separate units. One predicts the forward field, another predicts the adjoint field. And then we perform a near to far field transformation from the forward simulation to calculate the efficiency, which is defined as the power in the output direction over the total incident power. This is also the figure of merit that we care about. The adjoint gradient with regard to efficiency can be computed given the forward and adjoint field. And it is then used to iteratively update the dielectric distribution of the device. With the baseline method, where we just train the unit with data, although the error is relatively low in the field prediction, it is not low enough in terms of the adjoint gradient. You can see that for the same device we saw earlier, the gradient prediction is very off comparing with the ground truth. So clearly the baseline method is not good enough. And then I would like to introduce our method, which fixes all these issues. We observe that a good field solution should not only have zero mean absolute error, but also should follow the Maxwell equations. And in terms of the magnetic field H, it should follow the Helmholtz equation. Thus, one of the training objectives should be minimizing the difference between the two sides of the Helmholtz equation, given a predicted field. So we add a Maxwell loss term to minimize this physical residue, which can be computed by applying a Laplacian kernel onto the field matrix. Here we'll revisit the computation graph for calculating the loss. So this is what we just saw for the baseline method, where only the data loss is used. In the new scheme, we added this additional Maxwell loss to make sure that the opposite field obey Maxwell's equations. And we have a hyperparameter alpha, which controls the weight between the two loss terms. To summarize, here is what we use for the loss function in this data and physics-driven training process. Since the Maxwell loss can be calculated just using the output of the network, and it can be computed simply through a convolution process, it brings almost no burden to the training in terms of computation cost. So with this newly formed loss function, we again train separate units to perform forward and adjoint simulations. And this time, because the predicted field inherently follows the Maxwell equation, it is much more physically accurate. And as a result, the adjoint gradient has a much improved accuracy. You can see that for the same device we saw earlier, the gradient prediction matches very well with the ground truth this time. So next, we will see if this level of accuracy at each step works for an iterative optimizer. Here we first show the efficiency curve of a 100 iteration local optimization with an FDFD solver. And it gives us a final device of about 80% efficient. This can be viewed as a ground truth optimization, which takes about 7 minutes to finish. Then with the exact same starting point, we run this optimization with the baseline solver, where the unit is only trained with data. As expected, this one obviously does not work because the gradient at each step is very off, and the optimization can easily fall into a wrong track. By comparison, this is what a physically regularized unit optimizer gives us. We can see that this looks much more reasonable and comparable to the ground truth curve. And also this run only takes less than 5 seconds, which brings about a 100x reduction. However, note that the efficiency here is also the predicted value from the unit. So to check if the efficiency prediction is trustworthy, we plot out this red curve, which is sort of a corrected version of the efficiency by taking the device at each step and use the FDFD solver to calculate the ground truth efficiency. And we see that the two curves match pretty well. And this indicates that the physically regularized unit can provide pretty accurate results for both gradient and efficiency. So what we just saw is just an optimization for a single run. To avoid being cherry picking, we run 100 times of local optimization with randomly initialized starting point for both solvers. And from this performance histogram, we see that the physically regularized unit-based optimizer produces results consistent with the standard FDFD-based solver, and they share similar distributions. So until here, we see that units can effectively achieve an ultrafast optimizer. And what I will show in the following slides is that this acceleration can be even more significant for population-based optimizer, where tens of thousands of simulations are required. Here shows the scheme of a population-based optimizer recently developed by our group. The idea here is to perform optimization over a distribution of devices during each step, where a generative neural network is used to produce a batch of devices that cover the whole design space. Then forward and adjoint simulations need to be performed for each of the devices to calculate the gradients. And instead of updating individual device pattern in each iteration, the generator updates the device distribution by backpropagating all their adjoint gradients to update the network weights. Since all different device patterns share the same generator, the generator knows the efficiencies and gradients of the whole device ensemble, so that the distribution of the generated devices evolves as a group, as shown on the right. Therefore, more promising part of the design space will be explored in the next iteration, and the distribution of generated devices will be gradually converged to a high efficiency cluster. And in this way, local optima will be easily avoided, and it's more likely to converge to the global optima. So here with UNet as the solver, we perform this population-based optimization, which takes only about 10 minutes. By contrast, a FDFD solver takes about half a day. And the histogram, you can see here that after 200 iterations with a batch size of 100, the distribution of generated devices converges to a high efficiency cluster at around 80 to 85%. In this last part, I will share with you one of our interesting findings. It is well known that we can always increase the amount of data we use for training to improve the network performance. And this is true, as we can see here. With the data-only UNet, by increasing the training data set size, both the error in field prediction and efficiency prediction goes down. However, we can also see that the curve plateaus pretty fast. And if we again plot these curves, but for physically regularized training, you can see that from the red curves and also the orange dashed line, there is a quantitative improvement by adding physics, which cannot be achieved with simply adding more training data. In fact, even with 100K training data, the data-only UNet cannot outperform a physically regularized UNet trained just with 30K data. So to summarize, we present a physically regularized UNet field solver that can perform topology optimization 2 orders of magnitude faster than a standard FDFD solver, but with consistent results. And we show this for both local optimization and population-based global optimization. We've also shown that adding physics into the training process brings quantitative improvements, which cannot be achieved by adding more training data. And lastly, this study is funded by Packard Foundations, ARPA-E, and Applied Materials. Thank you so much for listening.
Great, thank you so much, Mingkun. Again, just to remind everyone, if you have any questions, please type it into the Q&A. I have an immediate question. To what extent do you think the UNet can solve for general configurations of structures?
Yes, in fact, here in this study, we just study a pretty basic structure, which is a freeform nanoregis device. But in fact, we've also tried with different materials and different thickness of the grating and then varying topologies. And it turns out the UNet works pretty well for this problem. We've also seen from Muskin's study that in fact he used it for 3D materials or 3D structures. And then that works very well for his case. So I believe, yeah, with the current network capacity, we're able to fit in freeform 3D structures.